Okay, well, just wanted to get my my 100 push-ups and other things out of the way for the day before it was the next day. There was like 20 minutes left. I'm like, you know what? It's not too late. We can crank out this and just write a little bit more code. I don't really feel like writing any more code, but let's just write a little bit more. So I think we need like a unit test for this file. So I think what we could do down here is create like a unit test section. We'll call it unit test section, and we will just do something kind of simple to test that this is working, right? So we'll say like AAC, or how about void. We'll say AAC 2020 PAINT5D unit test P5D OGL. Sure, why not? Or do we want to call it like since this is the file we're in, AAC 2020 P5D OGL unit test, it really doesn't matter. But this is going to be called by over here. So if we go to the unit test section here, we're just going to throw that in there somewhere. I don't know exactly where we're going to throw it in, but let's see. Where is this being called? Run unit tests, system data backup. How hard is it to back up this data? So it'd be a lot easier if we could just throw this into everything else. However, the unit tests are already taking a long time, so it'd be nice to just kind of like steal some of this and just say, you know, here's our system data backup right here, right? And then we're going to run the unit test code, and then after that we're going to do the system data restore. And yeah, we'll just take this, we'll copy it. So I don't really like the way I named it. Oh, system data restore. Oh, okay, got it. That's why it looks like that. Okay, got it. So, okay. And over here is going to be where it says run unit tests. Alright, we'll just kind of steal some of this stuff, right? So this is kind of clunky, but we're just going to get it running, right? So we're just throwing some stuff together here to get some tests. And the reason why I'm having this have its own backup and restore is so that I can call this in isolation if I want. And right here we'll just say I really don't care about the naming convention here right now. I just want to get this done. So here we're going to say, you know, extern void, and then have it right here for declaration, right? And this also is void. I don't know. AAC P5D OGL. How about UTC private? I don't know. Right. Okay, right. So then we can kind of throw this down a little bit lower where we can kind of forget about it, right? So we have this function here, and then down here we'll have this other function, void, also taking void, and then we'll do all our fancy stuff over here, and no, we can't do that. Yeah, so now that we have this, I want to call this function from over here somewhere, but specifically from wherever this is being called. So we have like a guard around this somewhere. Somehow we're guarding this, so let's look at, yeah, so this has a little guard around it. And what we're going to do is we're just going to say Within here, is this the init function? This should be the init function we have up here. Like, all this is in init? Yeah. So with init, we're going to say, that so I'm just gonna take note of the video ID. At vid IID is 86, and the time is, and let's call that 40, and always run this unit test the file. So this is going to test. I'm going to change the timestamp after I'm done writing this commentary, just because the timestamp is kind of out of is no longer as valid. Test the file OpenGL hackcode /P5D OGL. Alright. So it's going to test that file, and yeah, I mean, that's all it does, right? Yeah, so we're always going to, for now, the kill switch is not going to be able to get to this. We're always going to run this. Now, the include for this code, I don't even know where I put it. I put it somewhere in here, but I think I put it further down. I don't think it's up here. So let's look for the word include for a second, because depending on where the include is, so we're on 3042, and is the include above or below? It looks like it's above. Okay, cool. So because of that, alright, so make a note that this is what it contains. So yeah, we don't need a forward declaration because of where we included that. But yeah, we just want to run this. And for right now, we want just a quick, confirmation that we're in here. So we're just going to take this and put it in the logs like this. And see if we can kind of find that when we run, right? So we just kind of stubbed in a unit test. And we're not going to do much code here today. We're just going to, where's my, hold on, torch. Thought I had this open. So, oh, I see. I must have closed it. I must have closed it when I closed my timer. So anyways, let me keep my chat open, or not my chat, but let me make sure I can see what's going on here. So now we're on 86. I don't even know what part of PAINT5D this is. I guess it's part 19. Let me change my done. Okay. So yeah, unknown type. We'll fix that. So let's go back into the code here. And in this unit test section, we'll just kind of, we got U08. Is that the only thing we need? Looks like the only thing we need is U08. So we're going to just define U08 over here, and then we'll undef it over here. Okay, cool. We'll give it another run. And we just want to implicit function declaration, huh? Really? Oh, PAINT5D backup touter. Okay, this is coming from PAINT5D. That's why it's an implicit function declaration. Because, okay, So for that, we are going to use some forward declarations just to get this working. So, you know, it's an extern, and it's this function. I do not know what type this is. Well, I guess it's a U08 pointer. And what does it return? Does it just return anything, or does it not? I'm going to take a big guess and say it returns void, but let's take a look at it. Void, yeah. And it's a double pointer. Alright, so we'll just make this kind of forward declaration here so that we can use it, and we'll make a note of that one, right? So backing up Touter is a little bit different than backing up these other things. So let's give that a run and see if that fixes the problem. We are kind of breaking some patterns here. That's not our code. Hold on. Implicit declaration of function AAC 2020 PAINT5D restore. Oh, same thing with the restore function, right? So, right, the backup and restore functions are made in the same place, so that means we have to do the same thing here. So, extern void, and we want to take this thing here. We'll paste it here, and it's going to take a U08 pointer, like that. Okay, cool. Let's give that a run. Okay, so we're back in business, it looks like. Now, if we close this, can we find... So this is like good luck finding where that function is being called, because everything's logging everywhere. So what we're going to do now is, what we could do, instead of doing a log, we could just halt, which is hackish, but I just want some confirmation that we're actually getting to that point. And I'm pretty sure we are, but and even though we're in a different file, we're going to consider this file just an extension of PAINT5D. We just broke it up because we have so much stuff in this file already that we just broke it up for administrative effort reasons. So yeah, let's give that a run and see if we halt where we think we're going to halt, right? If we halt on that message, then we know we're executing this code, and that's all I really want is some confirmation. Yeah. So okay, so we are actually getting there. That's good. That is kind of a hacky way to do it, but whatever works. So what are we going to do in order to test out this function, right? Well, I think AAC 2020 PAINT5D get. I think all we really need to do is use PAINT5D put on a decent amount of values where, so something like this. For the tile quadrant, now these are going to be, how is this going to work? Because some things are going to use for, I don't know, int tq equals 0, tq less than or equal to 0, 1, or 2, so less than or equal to 2, TQ++, and for for the tile exponent, that's 0 to 7, yeah. Okay, that's 0 to 7. Let's just kind of loop over everything. For the layer is 0, 1, or 2. Oh, well, the quadrant is 0, 1, 2, or 3. Oh, my bad there. Okay. And for the local TX, local TY, I really don't care what that is. The only local value that we can accurately test is 0. That's why it would be easier to do X than Y. Okay, so it would be easier to, for the sake of testing and getting like every single pixel hit, for PX equals 0, PX is less than or equal to 5, 12 minus 1, and then PX++, duplicate that, do it on the Y. Okay. And AAC 2020 PAINT5D. So this should be the function that we need. And let's go look that up for a second, see what that is over here. So Glockfix to PainFix, we have the tile quadrant. Well, hold on. Oh yeah, because they're the outputs. So the tile quadrant, the tile exponent, the tile layer. The local X, the local Y, and the last things are going to have global Alright, so the last things are the global GlowTX, GlowTY. I think that might be more descriptive. Now the thing with putting everything here like this is not how I usually write code, and it also is going to take me longer because I can't do everything in one fell swoop like I usually do. So I don't know if there's really an advantage to writing it like this, besides the compactness. But besides the compactness, yeah, this is shit. Fuck this. So it's easier just to be like this. Bam, throw that in there, move that over, pow, pow, pow. Remove the types. U08s and I16s. That might actually be important. I'm gonna keep that for reference. Put this over here. Comment it out. Yeah. Yeah, being able to do things in fell swoops like this is really nice. Move that over there. So this global thing, whatever here, though, is going to be px, right? So, I mean, if we really want to, we could do... If we really want these variables, if we really want all these variables, we could do this, right? We could be fancy. And px, py, and these other things are outputs of this helper function. So we got to go like and, put an and around all that. And then you're good to go, right? Now, these ones shouldn't really have equals around them, so I don't know if I should really line it up like that, because then you might think that you do need to put equals around them. Or put equals there, right? Okay, so, yeah, let's, yeah. I think that's better. And knowing what types they are. Because things are gonna get kind of weird here, so I think we might want to up here. We might actually want to make a note of what the types of these are, because we're gonna have int 16 versions of everything, and we're going to have different versions of different things, right? In terms of the bit widths of them, and we're going to use them for different purposes. So in terms of general to specific in my variable naming, I think really we want to do like U08. I think we want to put these specifiers in the front this time, because of how it's going to be batched in terms of how I write the code. So we're going to say, we're going to take all these types here, right? And paste them up here. And so these will be for the original function calls. We'll use these. And okay, this is int 16. What is this? This is nothing right now. Okay, so int 32 might make sense. So this is pixel y, and up here is pixel x. Px, py, right? And we'll need a cast here, so I16, right? We'll cast it to int 16, and we expect that to just work magically, right? Okay, then once we have these locations, we're going to use the PAINT5D put function. So, man, we're using it in a lot of places. But yeah, you can see PAINT5D put wow. I have a lot of unit test code, so it's like all over the place. So if we really want to find it, we gotta scroll back to the top. Okay, so... okay. So when we call this... nothing is a... okay, there's no... we don't need the return value, we just need to set the value. And these are all U08 values, so it's good to know that. The tile quadrant. So we can take these U08 whatevers here. right? Like if we put U08 in front of here, we already have all these, right? Yeah, we already have all these. Now for offset dex and tile value, they are all also U08. So let's do U08 OSDEX. Okay, so OSDEX and tile value. What do we want to do? I guess, how about, like, let's just set them to something and do, like, a little simple formula for, just, like, increment them or something. You know, increment them, and then if we get to the limit, we just roll over or something. So, plus plus, and then, you know, if, this is, greater than 15, yeah, no, this is going to take more, let's put it down here. If it's greater than 15, then we roll back to 0, right? And then we need the same kind of thing for the tile value. Except the tile value is going to be 0, 1, 2, or 3, because there's only 4 bits. Okay, so just some type of code to generate some values to set in different locations. So we're going to set one value per pixel. Now, I don't really like that, because that's not going to help us test any of the bit packing features of this. So to test the bit packing features, let's get rid of OSDEX here. And we're going to set it equal to OS, and then OS is going to be like, what would make more sense? Yeah, it makes more sense here. So the offset is bit packed into the pixel. So os equals 0, os is less than or equal to 15, and os plus plus. And then we'll make like a os, whatever the heck, somewhere. We'll call this, I don't know, int32 os, offset index. And this os is os U08, so when we do the assignment, and let's get rid of this, the tile value, we can keep that tile value. We'll glue the tile value right up to here, like that, I think. But this offset dex, we're going to remove that and do a U08 cast of os here. Okay. Os dex, the tile value. And once we use the put, right, once we use the put, what we want to do is we want to also use the get and get the same thing. But rather than using the normal getter, we're going to use the getter that we've written just here, the getter that's going to go into the GLSL code, right? So it's like a very similar, it's a stripped down version, and it only takes int32s. And it doesn't take anything by reference, right? So this get right here, we want this guy here. And we're going to do two tests here. We're going to make sure that we get it. Use GLSL version of getter. Alright, so that's the difference here. And the tile value is going to be a U32 tile value. So let's take this and go U32 tile value. and it is going to be equal to calling this function with all the things that it needs, right? And all of these are int32s. So to make these int32s, we're just going to do a cast here, right? We're not going to worry too much about, right? Just cast it, and as long as everything's within range, that'll be fine. And these are all UO8s, so UO8 underscore, and now we have this, that, and this, okay, and then tile value, right? So we set this tile value, and then we expect to get this tile value back, right? So if U32 tile value is not equal to, or actually let's do not equal to over here, not equal to U08 tile value, and because we have these two different types, we should compare them by upcasting. So let's upcast to like an int32. Now, why we're going to cast to int32 rather than a u32, right? We're going to lose precision going from unsigned to assigned, but this value should be within a range where we're not going to truncate the value. And so this feels like the most reasonable thing. Or maybe we should cast to, if we really want to cast to something, maybe then IO8 actually makes sense, because then we can cast a common thing, but we lose precision here and here because of this casting to, because this is signed, this is unsigned, this is signed, so we're gonna split the range in half by casting to assigned. And I think this will be the most robust way to check that will throw an error if we lose precision by having values that were originally out of range, if that makes sense. Yeah, let's just do that. So if these are not equal to each other, then we fail the test. Failed. Okay, so this is our GLSL test of PAINT5D. And that's the first test. There's one more thing we're going to do. So we have this triple loop here. We're going to take this triple loop and we're going to take this triple loop and we're going to try to use our getters again with the exact same generation code. Right, so we're going to take all this stuff here and go over here. And we have this get here, right? So we're going to take this stuff here and we're going to do one more check on that getter. We're going to say that this U32 tile value should be equal to this U08 tile value, right? Because we generated this U08 tile value right here, and it should still be equal to that. Now, hold up a second here, though. We're checking this against that. Okay, that's what we put. Yeah. Oh, no, that makes sense. Okay, that's good, yeah. So the reason for this is that some of the collisions with the pixel addresses of where we put the tile value, those collisions aren't gonna, if we put something and then immediately get it, we're not going to find certain mistakes, right? Like stomping memory. We're not going to find a memory stomp. So, run a second time with only getter to detect right. So the reason we're going to run this a second time with only the getter code, and regenerating all of the tile values that we put down is because this code is going to detect memory stomps. It's going to detect if we're trying to set the same, if this combination of tile quadrant, tile exponent, tile layer, local tx, local ty, and offset dex, if there's multiple combinations or permutations of, I guess combinations, combinations, yeah. If there's multiple combinations of these values that map to the exact same pixels and exact same bytes of those pixels, then this loop will be able to detect that. It'll be able to detect that. But however, this loop up here will not be able to detect those memory stomps, because right after we put the value, we get the value. And so if there's any type of error due to overwriting memory accidentally, this first loop isn't going to catch it. So we need to run the loop one more time using the exact same structure, right? We can't change any of this around, otherwise it's not going to work, and regenerating the tile value in the exact same way. And if we run this loop in exactly the same way, then we expect this tile value here to be exactly the same as this value we're getting here, right? So int32s, this is a u32. Yeah, so that's basically all we need for this test, right? It's pretty simple. Let's give that a run and see if we're lucky or if we're just not lucky. So I'm sure we made a syntax error somewhere, so I'll have to fix that first. Error, unknown type name I32. Oh, so not a syntax error, but we're going to have to define some things, right? So we got, like, int32's IO8. So I32 IO8, probably U32 as well. Yeah, there's a U32 val here. If there's a U32 val, then where the heck is it here? So over here we need to, for return, yep. Okay, so U32 tile value. Let's just remove all this crap. So yeah, we need to add a lot of stuff. So define IO8, define U32, define I32. Anything else? Do we have an int16 down here too? I thought we did. One of these is an int16, right? Yeah, this is an int16. So we need an int16 as well. So we got a lot of stuff here. Let's make this all line up kind of nicely. And let's create a checksum here, because now we got a lot of defines. Okay, paste that. Okay, go down to the down here for a second. Paste this here. Change this to undef. Add extra space. Okay, cool. So we're about ready to give this another shot. And I'm hoping this will just work. I'm hoping that we'll just have accomplished this and get to move on to the next thing. Unknown error, type name U08 Ostex. So we just forgot some stuff as we were writing this. So Ostex here. The U08 tile value, you remembered. Oh, hold on. We didn't forget about it. We just forgot to actually, like, write the code all the way. So, yeah. Implicit function declaration, huh? Okay, so there's a lot of things where we're just gonna have to... I honestly do not want to have to forward declare this. Right, because if I have to forward declare this, this is just going to be a pain in my butt. Just because of how detailed the forward declaration for this has to be. I don't know if I want to do that. Like, it's nice having it here. But, you know, if that's... Yeah, I really don't want to have to forward declare any of this. So, you know what we're gonna do? We're not gonna waste our time trying to forward declare all this stuff. We're just gonna say, we're gonna throw this. Just gonna throw this down here. And we're gonna call it P5D. Right, so it's the unit test code P5D OGL, right? It's not the best solution, but what's the best code? Well, I don't know. What's the best code? What's the best code you can write? What's the most efficient, fastest code you can ever write, right? It's the code you don't write, right? So by moving it over here so I don't have to write a forward declaration, maybe I'm just taking that saying to an absurd level. But, yeah, but now if we have this over here, we don't have to worry about the problem with that, right? And we still have this OpenGL, and now we have kind of like only the code that we want to paste into OpenGL, kind of like in isolation, except for, you know, this stuff here. Yeah, let's give that a shot, see if moving that into this file makes it a little bit better. Implicit declaration of function AAC 2020. So because we did that, we have to now forward declare this unit test where we're calling it, because it is no longer available to us just like here. So we got to do you know, extern void, and this is also void, and EU, is that extern U32? I'm gonna put a define right here and then undefine it right here. It'll also make it easier to know that this commentary goes with this code, right? So we're still on 8.6. Okay, so we've changed it up a bit. We've moved this unit test code into the bottom of the PAINT5D file, just so that we don't have to do a whole bunch of forward declarations for some of the functions we're using. It's just going to be easier. That's why I put it in here. And also, another change we've done is now we have a typedef for, or sorry, not a typedef, but a define for extern void, so that we can kind of shorten this line so we can get this nice and lined up like this. And yeah, so let's give that a shot and see if that can run, or if we have some other mistakes we got to fix up here. Okay, ASC 2020 PAINT5D Glockpix to PAINPix. Implicit declaration of function. So I think I may have kind of typed that, and maybe that's not quite right, or it could be where it exists. I don't know. Well, hold on. What file is that coming from? Is that coming from PAINT5D? Is that coming from my unit test code, or where is that coming from? Okay, it is coming from my unit test code. So that probably means that I spelled that improperly or something. Or it's probably a private function, I'm guessing. So Glockpix to PAINPix, this thing. Yeah, it's a private, so go back. It makes sense that it's private. Okay, private function, got it. Alright, let's give that another run. Unexpected blah 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 in paint5d.f. It's saying 7950, huh? Oh, not enough semicolons here, my friend. Okay, let's give that a shot. Did I say semicolons? Because I meant parentheses. 7983, probably the same deal. Yeah, because we cut it and pasted, so of course. Okay. Oh, looks like it's compiling. Cool, cool, cool. Okay, so fail GLSL test of PAINT5D. Okay, so our unit test is failing, and it's the first one's failing. So the first thing I want to know is what these are, and let's just do this. So we're going to make some int 8 versions of these. All right. So this equals that, etc. And we're just going to use these so that when we are echoing out or printing out the values here that we're comparing, we have a little bit more assurance of what we're looking at and when we print out the values. Actually, hold on. Well, I can just take this, rename it to 1 over here. Okay, and then we can take these. Oh, well, that is ridiculous. IO8. I just want... Oh, I see why. Okay, never mind. Because they're both tile values, so there's the IO8, there's the U32 to IO8, and there's the U08 to IO8. That is... Those are some weird variable names that I gotta say. But I see, okay, I see... So over here is going to be for comparison, right? So... Yep. And I think that's all we need. I mean, while we're here, since we're here, I mean, we could kind of be like, we could make a nice little section, say, hey, we're declaring variables over here. We could indent this nicely, right? We could take some time to be like, hey, since it did crash on it, let's take some time to correct the code and also make it a little bit nicer, right? Look, we got a nice little section here. Isn't that nice? Okay, so this loop here then, but then do we gotta make a section for this? Let's not get it carried away here. Let's just get this working first. Yeah, so all we wanted to do is say, you know, printf these different values. Alright. And let's take that same code, put it over here, because we're gonna... we got it, so we might as well just paste it in here. Okay, cool. So let's give it another run. It's still gonna fail on us, but now we can kind of see a little message of what's going on here. Unexpected before we don't know how to write code. That's what that says. So that's on 7... It's the first one, most likely. 7957, 7965, so right here. Oh, yeah, so, yeah, this is, called, sometimes I format things weird, but then I forget that, you know, just, yeah. Okay. Okay, we got a tile value of 3. Okay, so now the question is, because these tile values are different, what I would like to do is say, okay, is it my new version? Is it my rewrite that is failing, or is something else failing, right? So let's do that. So this put function here, do you want to call the original getter? Sure, why not? So the tile value that we're putting here is this UO8 tile value, right? We don't really need to do that. We can just say, we can just take it and print it off, right? We'll take this and also use it down here as well. It's a lot of redundancy, but oh well. Make a note of what OG stands for in this code. So yeah, OG, just what I really mean is, you know, it's the original function, right? So we're trying to test this GLSL version, which is the transcription of this function. And now that we have a test failure, we just want to know, hey, does the original fail too, or is it actually an error in our transcription, right? So we can also say, like, if if this value is equal to the value we're setting down in this loop, which is this U08 tile value, so if this value is equal to this value, then we just have some type of transcription problem between how we wrote one function to the other function, and that's not too bad. It's still a problem, but it's not as bad as if we get this problem. So let's just make a note of how bad the problem is, and that was inside of the. Yeah, so let's just paste this here. All right, let's give that a run and see what we find, see if we even use that correctly. So first of all, we have to spell printf properly. And this is why I wanted to do a rewrite in C code first so I could write some tests for it, because yeah, transcription problem, right? That's not as bad as what it could be, right? Like, it could have been much worse than a transcription problem, right? I think that is probably the best we could hope for in terms of what's wrong. But it does mean that we have to write some more tests, right? Yeah, so transcription problem, and the OG tile value is 1. And the U08 tile value that we set down, that is 1, but the value we got back was a 3, right? So it's something about the, and also it happened in the first set, right? So it's not even a memory stomp issue, it's just something else. And so now we have to figure out where we went wrong in that transcription. And the thing that sucks with that is that means that we were hoping we just have to test this one function and be done. But because of this means we have to go in and kind of like test other functions, right? We gotta test the other individual functions to see which ones might also be failing us. So now we're gonna have to say, like, this function now needs to be broken up into more functions, unfortunately. So we're gonna have to say, like, first we can copy this, and so what are we testing here? We're just testing the get function, right? That's what we're testing, the PAINT5D PAINT5D get. So we could kind of name it as PAINT5D get, and that is a very obtuse name. Yeah. Once this test passes, right, so I want a little note here that in terms of this test code here that we're writing, our goal is to get this running and running properly by passing its test. Now, we may test other sub-functions that are used within the PAINT5D get function within this file. So we want to test this function. We want to get this function right here working. So we may want to test like these other sub-functions, like this function and this function. But we don't really care about these functions because if the main get function, if its test pass by inheritance, you could say the other functions are automatically correct. Does that make sense? Like if the parent passes its test, then its children also pass, right? If a chain can hold a payload without dropping it, then the chain has passed, say, its test, right? And if that chain can pass its test of holding the payload, then you don't have to test the individual links of the chain, right? Because the entire chain works. So it's the same thing here. Like, all the sub-functions used by this function could be thought of as different links in the chain that create this function. So once we get this function working properly, we don't need to test the individual components anymore. So at vid IID 0086, and the time is 6:35. Okay, restating for the camera. We only want to get this function working. This test code, we want this test to not fail because it tests this. And this is the function we want to put into the GLSL code. Once this works, we know that all of the sub-functions also work by proxy. It's like, you could think of this function as a big chain, and we're testing the chain. And if the chain works, we know that the individual links of the chain also work, right? Because if one link of a chain is broken, the chain would cease to be a chain, right? So all we need to do is make sure that we can get this working. However, it's failing right now, so we do have to go in and test out some of these sub-functions until we figure out where we went wrong with our math, right? So we went wrong somewhere. We don't know exactly where, but now we have to kind of figure that out. So we got this main function. And now we just got to figure out, well, why is this wrong? What went wrong, and how can we fix it? So the other thing I might want to do here is say, how far did we get before this code failed on us? So like PX and PY. What were PX and... Ooh, hold up. Yeah, what were PX and PY? Because maybe this code actually works, but... we used one of the invalid PX, PY locations. So let's, did we do all that for nothing? Well, whatever. So hold up. So yeah, let's hold up here for a second. Printf px py %d. Actually, %d %d, and then \n. So if we print off px and py, are we on one of those invalid pixels? Because our loop, we forgot to exit or skip over the invalid locations. So we might actually be lucky and not actually have any failure at all. Well, that would be nice. So pedantic, whatever the heck, because I wrote my functions this way again. I always write my functions this way, but I'm not allowed to do that in C code. Okay, so that would be nice. So if this fails and we see that px py is like 255 255 or 255 511 or something like that, nope, we're not that lucky. Px py is failing on 0, 0. I'd say that's a pretty big problem, right? So you're trying to set a 1, and you're getting back a 3. So that kind of makes me think that maybe the problem is with the bit packing, but I really don't know, right? It could be anywhere. So what we're going to do before we forget about it, because now we realize that there is another mistake in here. I mean, a lot of this is identical. We also need if 255 equals px and 255 equals py, we want to skip over it because it's invalid pixel location. And there's a lot of so let's go from in scan line order. So the next thing we want to do is go over to the top right. Then we got to go to the bottom left. And then we want the bottom right. Okay. Px and py. So we want to take this code that's supposed to be identical, copy that, go back to this other section where we said code identical in both loops, and bam. Okay, and we might want to make a note of this. ID. Oops. Skip. Yeah, so we need to skip the configuration pixels. Let's just call this 12. Yeah, we want to skip the configuration pixels. So this is the top left configuration pixel, the top right, the bottom left, and the bottom right. And if you want to know where that is in the diagrams, we can go into PAINT5D data, and we can scroll up here. And in this diagram, our configuration pixels are right here, 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 and here, in how we're partitioning out this 512 by 512 bitmap. And those pixels don't actually do anything for storing tile values, but we can use them for configuration settings, like palettes or whatever we want to use it for. So we're going to skip over those. So now that we know we're going to skip over them, we also want to paste this code in its identical section. So over here as well, we'll keep the exact same timestamp. That's fine. Okay, so let's give this one more run, and then I think I'm just going to be done for today, right? I just wanted to do like a little bit more to be like, hey, I know what the next step is. I wanted to do just a little bit more just to kind of move things forward by a little bit. So transcription problem, pxpy 00. So why don't I have... I'm just going to rename these to transcription problem red, and then down where I kind of copied all the code, I'm just going to be like transcription problem blue. Just to make it a little bit easier to kind of know what section I'm in. Because this is a lot of redundancy here, right? A lot of cutting and pasting. So transcription problem red, pxpy 0, 0. The OG val is equal to this, right? That's why it's a transcription problem, because the OG value is equal to the value that we actually set. So the original code that I wrote is correct, but the code I transcribed is wrong. And this is why we are doing a rewrite for code that we're going to try to paste into the GLSL, because there's a lot of potential just to get this wrong, right? Now, I would like a way to not have to write it like this, like do this weird hack of writing it in a way where I can just easily cut, paste it. It'd be nicer if I could just, if I could... Let me think here. I really want to be able to stringify all the source code and put it into the executable. But that's a little bit too difficult. There's undefined behavior if you try to do like a stringify macro with an include, and it's not portable. So yeah, we are going to do it this way. We're just going to rewrite the function, and then we're rewriting it in such a way where we can take it verbatim and just cut paste it into our GLSL code, right? So we're going to take this exact code, and instead of using any type of build system or whatnot, we're just going to, once we test this code and we know it works, we're just going to cut and paste it into the GLSL. So let's search for kind of like simple mistakes first. You know, hope we got off easy. And just say, so like, we know that X's and Y's are things that we often mix together. And maybe we weren't careful enough. Maybe we kind of screwed this up, right? So that's something we could look for. So we're just gonna spot something where we just have these two colors. The other mistake is, did we add these values wrong? Right? That could be a thing. Or. No, D is diagpix, that's fine. Do we have the correct texel fetch? Ooh, our texel fetch isn't correct, is it? Yeah, our texel fetch isn't correct. That's what's wrong. So if we look at our texel fetch stub here, our polyfill for the texel fetch is totally wrong, right? Let's see what this is. Yeah, this is wrong. And yeah, that's wrong. So our texel fetch is wrong. So that's nice to know that we transcribed it in the part, and we at least know that one reason why the code isn't working is because the part we transcribed is improper. So, you know, this part we copied, right? So we get the global location and turn it into an index location, multiply by 4 to get the component. However, this isn't right? Because we need to actually get the pixel components. So let's just do this. Let's go, let's say, first of all, let's get rid of this return. And define, CP. Guess what? This is glowcom plus 0. And some other things as well. So we need to actually bit pack our pixel here. Right, we totally forgot about that, right? We're like, oh yeah, we're done. No, we're not done. We were done in the case of... Yeah. And then we have to think about how this is being used as well. So if we look at where this texel fetch is being used, we called it TF in here. So we get this var U32, and we shift it out, right? Yeah, I mean, that's right. I mean, shifting it out by the amount, by the offset index, and we can actually check to make sure that's true. Like if we look at our diagram, right, we won't consult the code, we'll consult our diagram. And you notice that the offset decks were numbering the actual bits like this. So the 15th bit is over here, so if we want to shift it out, we got to shift it out 15, right? So we go shift this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? It takes 15 jumps or 15 shifts to get the 15th out, right? So that's good. I mean, this is good for unpacking it. So how do we bit pack it in, right? So, well, first of all, let's actually look for some bit shifting math where we're actually doing that, because I know we have some unit test code where we're already doing that. And it would be nice to just find that code already. So U32 var, right? And did we call it U32 var in here as well? Because it'd be nice if we have some consistent naming here. No, we didn't call it U32 var. What did we call it then? Hold on. Var U32. Okay, hold up here. Let's be consistent here. U32 var. Var U32. Okay, no. So var U32 is off limits. It's supposed to be called U32 var. So anywhere we find this, we're just going to replace it. Replace that, replace that, replace that. It's U32 var. Why? Why is it that way? That's just the way we decided that it should be called. And we want to avoid... right, we want to avoid fractionating our variable space. So if this is U32 var here, this should also be U32 var here, because it represents the same exact data, right? Okay, so now that we have that there, we can go back up here and say, hey, we could just take this and copy it, right? We could, we can just take this, because we already know this should be correct. We could turn this into all capitals since it's a, you know, a define. And we could also So we could also make a note of where we copied this from, right? So it needs to be 1, 2, 3. How did I do this? Yeah, 1, 2, 3. And 30. Let's not do that just yet. Bit shifting code copied directly from well, where are we? Where are we in here? We are in... So this is where it's copied from. And we could, like, since it's an identical block of code, what we could do is we could, like, kind of, like, shove things into, like, includes. But I find when I shove a whole bunch of code into includes, it makes the code really unmaintainable. Because I've tried that before. Where it's like, oh, we just copied this identical thing of code. Why don't we kind of, like, why don't we... You know, right? If this is going to be so identical, why not put it in a define, right? Why not put this into its own file and reuse it in the different sections, right? And you'll be like, yeah, that makes sense, but it actually doesn't, because it just makes it a lot harder to follow the code, adds more administrative effort. So we're going to do something a little bit more ugly, and also we changed this to all capital, so it wouldn't even work. But it adds a lot of administrative effort. I mean, we could, you know, make this lowercase and make this define lowercase, so we could still do it by making this an include and making this include to a different file, but I find we just get, it just burns me when I do that. So what we're going to do here is we're just going to say, you know, add paired code 2021 0114. Where do I want to put this? Let's say paired bit packing code with the date. And then we can put this right here. Like that. And we'll use that to kind of identify that these two pieces of code are identical. So if we ever want to find these two pieces of paired code, we can take this text and do a find in files, and we're going to find it in only 2 files, right? Or only in 2 places, right? It could be in the same file, but we're going to find it only in 2 places, right? And yeah, I think that will help us identify where this came from. But yeah, so Okay, cool. So let's change the timestamp here. So 1 hour, 29 minutes, and 10 seconds. Okay, so right here, this bit shifting code has been stolen from this file right here. And if you actually want to find where that is, you can just search for this string here or this string here. These strings only appear 2 places in the entire code base. Right, so we've dated it and gave it a short description. So it's paired code, so paired code. So it's only going to show up in 2 places, right? That's why I say it's paired code. And yeah, this is just the proper bit shifting code to bit pack all of the individual components within our byte array to reconstruct the pixel, the U32 variable, that we need to return from this texel fetch polyfill. So now that we have it, let's just return it over here, right? So return the U32 var. So I honestly have no clue how that's gonna help us. Oh, I guess that makes sense. So we're getting a 3 when we should have had a 1, right? And that's probably because this component here, we were originally just getting this component here, but look, it shifted over all the way over to the left. So now, it looks like the bits that we care about, I don't know, but I see how it could have done it. I see how we could have got that mistake from this code being wrong. The code was wrong, and we fixed it, so now we're going to hope that our unit tests just work and that we're out of here. And that we don't have any more stuff to fix, right? So let's give this a look over here. So 0, 1, 2, 3, 24, 16, 8, 0. So these are proper, right? All multiples of 8 for the different bytes within the U32. We cut and pasted this, so we're pretty sure it works. The things we really want to worry about are this. This is an X, this is a Y. We take the stride times the Y to get the number of full rows, and then we add the remainder, and that gives us a one-dimensional index value corresponding to the X and Y. That makes sense. We gotta multiply by 4 because there's R, G, B, and A, right? 4 component color. So there's 4 components per pixel, 4 bytes per pixel. So now we have a global component index. This global component will point at the red. So we have the red as an offset of 0, green, blue, and alpha, because that's the order they appear in, and that's why they have these different relative offsets. Excellent. So what else? I mean, it all looks good to me here. I mean, I really don't know what else we could do to assure that, you know, nothing is wrong. We fixed something. That's good. Now we're just hoping that that'll be all we need to do, and our test will just pass, and we won't have to test any of those sub-functions. I really hope so. Well, we have to declare that variable as well. So let's go over here, U32 var. So let's just say U32, and it's U32 var. Output 32-bit pixel value. Okay. Alright, let's give it another run. And once we get this compiling, if it still doesn't work, I'm done for today, right? It's just like, we didn't just want to give up so easily. We're like, hey, let's just take a little closer look at this and see if, oh, hey, we just triggered our full test. So I just know by how long it's taking. So we made it so that we don't turn off our test. We just make our test kind of like randomly execute every once in a while. And, you know, this would be kind of a good way to do, like every time the random test pops up, we do like push-ups or something. So we're seeing PXPY, and we're getting 0, 1. So now it's not the first pixel, it's actually failing on the second pixel. And we still have the same kind of problem. So that's better. It's better. But yeah, we're still failing on... We're failing on the second pixel now. Excellent. On the, or actually, hold on. PXPY. Let's change the order here. So, when we look at if we look at this code, we're not going in scanline order through the tests, are we? Oh, wait, no, the tests are over here. My bad. If we could look at the test code for these functions, we're going px and then all the y's. So we're not going in an order that really makes sense here. I'm surprised that everything for... So I'm going to move this, and the thing is that we move this, we got to make sure that we keep the same for the other test. Right, we got to keep this block the same, identical. So, order means so if we want to go in scanline order, then we need the y to be on the outside of the loop. And from looking at the code, what I'm finding kind of interesting here is we just fixed the bit packing, and because it crashed on the second pixel, I think the bit packing logic is actually correct, and it's actually about locating where to read, which pixel to read. But I think the bit packing logic is actually correct now, and it's just reading from the wrong physical pixel. Which would make sense, because we just fixed the bit packing logic. Let's go into... Yeah, I'm a little bit tired, so let's... Yeah, I can't even find my documentation. It's right here. Yeah, I'm a little bit tired, so... I just want to make a note of what I mean by this, in case the sentence was not obvious. The sentence is probably obvious enough, but... Let's make a note of this before we leave, right? Okay. If you want to loop over x and y coordinates in traditional scan line order, left to right, then top to bottom, you need your y for loop. So let's take an example. Okay, that's just what I meant. Okay, let's give it one more run. Just to make sure... Let's just make sure that this code... I don't know. Just make sure that it's running how you expected it to. Oh, actually, we changed around the x and y, so we're expecting... Oh, we're on the long full test again. We are expecting that it does not fail on the first pixel, that it actually somehow gets to the second pixel before it fails, which tells us that the mistake is probably in the... So yeah, so this is interesting. We actually get to... So we can see px, py, and this is why I changed it around, because remember we failed on the second pixel? But if we do all of the x first before we swap to y, we see that we failed on 64, 0, right? So we got pretty far before we failed. So that's interesting, because that tells us, if we look at our diagrams, right, to fail at 64, that means we got like halfway through, this 128 by 128 block, and then we were like, huh, we're not actually in this area, right? We decided we're somewhere else for some reason. We, it could be a lot of things, but I think it could be a lot of things, but we know the bit shifting is probably correct. We know the bit shifting is probably correct, and that it's something else, and I do want to stop, but I just want to... If it's easy to... If it's lower hanging fruit than I realize, I want to get it now. So, the other piece of low hanging fruit we could kind of look at here is, like, this table here. So, why do we have the maximum coordinate? And if 0 equals the tile exponent, then the maximum coordinate is 128 minus 1. Otherwise, we have 64 minus 1. So the tile exponent is 1 in this case, right? It failed on... does it fail on 64 or does it fail on 63? That makes a big difference, doesn't it? Because if this is failing on 63, then that means the tile exponent is 1. That means it has failed once the tile exponent size has changed, which means maybe there's something about the tile exponent math that we're doing wrong. And there's probably a lookup table. There's 2 lookup tables that use the tile exponent. So there's 2 lookup tables we could check. So it's failing on 64, 0. I mean, that still doesn't necessarily mean the problem isn't with tile exponent, but I don't know. I'm less confident of that because of this. Or it thinks it's in one tile I don't know. If this math was off, we would have a problem, right? This is the stuff we kind of like... This wasn't a direct hard code, so let's look at the math for that, right? We have a little lookup table, don't we? So diag picks to whatever thingy is. Let's take this, move it over here for a second, and see what we have. So let's just throw this into a calculator and just double check these values. So the first one is 128, right? So, or the second one, I should say. The second entry is 128. So the tile exponent is going in here. Oh, hold up here. Yeah, because when we use this table, when we use this lookup table, so I think this is the wrong... I think we did the wrong function here. Hold on. Oh no. So tile exponent to diagonal pixels. Here's the tile exponent. It's going into this lookup table right here. Eight is invalid exponent. Yeah, so it is going into here. So that is what we're looking up. So we got 128 right there. If we do this, we should get a 64. Oh, not 64, but we should get 192. So we got 192. So all these look good here, right? 0, 128, 192. Like, all these things look good. So these are... Those look good so far. Now, how about this thing here? How about this? What is this? Is this 224, or did we screw that up? 224. Okay, that's 224, 224, 224. Okay, cool. Okay, how about this next one? Is it 240? It's like 240 to me. Okay, what about this thing? How about this number, this thing here? $248, that makes sense. $248 makes sense. Oh, hold on. Okay, how about this? I mean, I think I'm painstakingly checking something that is 252. Is that 252? Yeah, 252. Okay, now this last one. I mean, it's obvious right here from looking at it. 254, 254, yeah. So, I mean, that looks good to me. That doesn't look like a problem. Right, this else here is going to give us an invalid value, but that's only if, you know, the tile exponent that was inputted here was invalid in the first place. Otherwise, we set diagpics to the correct thing, right? D is for diagpics. What we could do is we could set this to a trap value, right? We could say diagpics equals 999. Right, we could do that. But I don't think that's the problem. However, by setting it to a trap value like that, we might actually, if there is some type of mistake, we would see a different result here in the function. We would see like something else happening. So we could actually, yeah, we still get 64 and 0. So I don't think that's the problem. Now, we could set this to something else ridiculous as well, right? We could set this to, you know, 9001, right? We could just set it to something crazy and see if the resulting failure is any different, right? Because that would tell us that the tile exponent that went in was somehow way not the correct thing, right? So we still get 64, 0. So I really doubt it that it's that. Yeah, so the only way we're going to be able to fix this is to start testing other functions, right? And the test can be pretty easy, right? Because now all of the tests that we need to do, they don't need to be too hard, right? All the tests can just be like, hey, we already did the tests for the original functions. We're just testing these transcribed versions. We're testing these rewrites of these other functions. So in order to test them, all we have to do is cross-check them against the functions that they're rewrites of, right? So it's really easy. We just run both of them at the same time and see if they get the same results, right? Run both functions with the same inputs and make sure that the outputs match because they're transcribed versions of the function. So the code for this is pretty easy to do. It's just I don't want to write it right now. I'm just tired of this. So we're gonna stop here. I just wanted to get enough done for today. Also, we kind of leaked into another day here, so let's look at our push-up screen here and say we're at 2 hours. How about trying to get like 40 more push-ups in, right? So total today 100 of each. So the week total is 310. So what we're gonna do now is we're gonna say, you know, today is sure this we're logging this as yesterday. Or do we want to log it as yesterday? Or do we want to say that this is a new day? I don't know. But we're going to say the stream is about 2 hours. And total today... Well, not if we do... Do we want to build this as... Do we want to build this as today, or do we want to build this as tomorrow? I think it'd be easier to build it as tomorrow because we already got our 100. So Monday, Tuesday, Wednesday, right? We're at 300. So you've gotten 100 for each day so far. So it would be easier if we just kind of build this as tomorrow. And 2 hours, 20 for each. So we're going to do 40. 40 today. We're going to add 40 to here to make this 50. Okay. And we're going to do our push-ups and stuff, and then we're going to stop the stream. But we're just going to... But we're going to just leave this here. Have a record of us doing our push-ups. Yeah, so let's get those done, and then let's just call it a day. We know what we need to do. We need to just write some more tests for those transcriptions, and then try to paste that code into our shader code and see what we can get going here. So let's start the timer and do 40 of everything. 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Alright. Only 10 minutes to do all that. But we're gonna have to keep it up for a while. I had to get rid of this extra weight. Lockdown kinda. Yeah. Alright. So we're out of here. I guess let's look at the agenda screen though. So the agenda screen, so we're really not doing number 10. We're doing something similar. We're kind of like hackishly writing code. So let's actually, so 10, we're not really doing 10, right? So we decided that one of our goals is to have a single executable that doesn't need like an installer, doesn't need any special files. It's just everything is packed in there, ready to go. So 10 really is finish P5D OGL test code. Right. So number 10 is really finish P5D OGL test code. So we can take that code, and once it's tested, we can just paste it directly into our shader code with minimal changes. If we have, if we've kept the code simple enough, it will be valid GLSL code, right? So that's an advantage of writing C, because C and GLSL are basically they're almost the same thing, but not quite. But we're going to take advantage of that, right? And it's going to be kind of a hackish, ugly. It's going to be an ugly kind of hack for the way we're doing it, but I think it's gonna help us. So that's the way we're going to do it. And we're out of here, because I didn't really want to do any work, but I thought, hey, well, it's on my mind. Why don't we just do a little bit of stuff, get some stuff done, right? Because I think that every time we think about, hey, could we do a little bit of code, those little things could add up, I think. So I'm going to keep on trying to do stuff like this. All right, later.